Now, if we move on to types of acoustic analysis, because you can, as an acoustic engineer, you can always choose to be either a test engineer or a simulations engineer. So now we have seen about the acoustic testing briefly, about acoustic testing, and then now we will see a little bit about acoustic analysis. In acoustic analysis, we have basically three types of acoustic analysis. In principle, most of the companies, they do only two types of acoustic analysis. That would be mostly vibroacoustics or aeroacoustics. Vibroacoustics is something which you do inside your structural mechanics tools. So you do a modal analysis, so to get the eigenfrequencies, the natural frequencies, and then based on these frequencies, you can measure the sound pressure within the fluid around it. So the fluid is static. The vibrations will be captured as a pressure around the part within this fluid, right? So it's basically structural. And the aeroacoustics, this is more CFD. So it's computational fluid dynamics. So in here, the acoustic fluid is not static, but your structural component is. So that means we are measuring the sound based on the flow of a fluid. So this is, simply put, it's a CFD. Okay, you might ask, okay, but in reality, it is not just structural or not just computational fluid dynamics, but it can be a combination of both. And you're right, this is why we have a different category, it's quite new, and it's called vibro-aeroacoustics, which is a combination of both. And it's quite challenging, and it's very complex to build such models, and very few companies are doing it right now, and even not all software codes available support this feature. This is something which is quite new and also very advanced. Basically, for the acoustic analysis, we have different strategies. We have a boundary element method, finite element method, could be also a combination of both, which is a tool called Acron offers this. They have a combination of both. To give you a quick idea, I'm not going into detail for today, 45 minutes is too short for that, but to give you a quick idea, what we do is we take our part and we create a finite element mesh for both a fluid and solid part, and we build 1D elements here for the infinite space. So the finite elements, the mesh you got here inside it, this is finite element method. And what you got here around the boundary, the 1D elements, these are called infinite elements in acoustic terms, is boundary element method. So we combine both, and this is very popular nowadays. And in fact, we are mostly doing this kind of analysis in between. So it's a combination of both boundary element and finite element method. Okay, but if we talk about the differences between boundary element method and finite element method, the major differences that you see on the screens, boundary element method is quite easy because most of the times it's line mesh. And with FEM, this can be a bit time consuming because you got, mostly if you're doing a simulation in 2D, you have a lot of elements. You can imagine how it could be with a 3D mesh. And sometimes you have more details, but when you are meshing your acoustic mesh, especially the fluid mesh, you should be really careful to avoid any triangles. So no tria elements in the acoustic fluid mesh. These are deep details, but technical details, but we can continue. Okay, the second point, we have very few degrees of freedom in boundary element method. In FEM, we got a lot of degrees of freedom because it could be a combination of both structural and computational fluid dynamic boundary conditions, right? But when you come to the computation time, the boundary element method, it requires a lot of time. But the FEM can be really faster. And it can also be because nowadays the parallelization, the parallel computers, they are capable of doing FEM much better because finite elements are much easier for the equations, to solve the equations. Okay, and then the coupling with existing finite element simulations is very difficult with BEM, boundary element method. But with FEM, as I mentioned, even your CFD mesh is a finite element mesh. So it's quite easy to combine both meshes to perform vibro aeroacoustic simulation, for example. And this can be easily coupled. So the coupled simulations are quite easy in case of FEM. And as I mentioned, nowadays we have a combination of both. So we have eliminated the disadvantages in BEM, and we have a good combination. So we have more advantageous strategy nowadays. So now coming to the main part. So how can an acoustic performance of a part can be increased? I think most of you are already familiar with structural mechanics, the structural simulations. What you do is you get a part from the developers or the CAD department in your company, and you perform a simulation, and you check for stresses in case of structural simulations, or the sound pressure in case of acoustic simulation. And you have a limits in case of structural. It could be your yield stress of your elements, yield stress of your material, or ultimate tensile strength of your material. So if your stresses are beyond these levels or these limits, you can send it back to the developer, or you can either optimize it for yourself, or you can send it to the developer. What you do is you take some necessary steps, like increasing the radiates, fillets, or whatever it might be. So you'll optimize your geometry, and then you simulate it again. And once your stresses are below the limits, your part is optimal. And this can be sent to the production team to create a prototype, which can be tested later. And this is how you can increase the acoustic performance of a part. So you have to optimize the geometry beforehand, right? And then another possibility is by eliminating or minimizing excitation sources. You can think about a small example. In your car, you have different types of moving parts. It could be motor or brakes or anything it might be. And if you need anything additional, like some extras, nice to have features, but they are noisy, you can eliminate them, for example, if it is only nice to have. Or if it is a must, you can minimize the sound coming from those parts by optimizing it somehow. And yeah, another possibility is to, of course, insulate the area around your noise source by means of some absorbing materials. We have a lot of absorbing materials in the market for automobiles. So you put some insulating material around the sound source, this noise source, and this will absorb as much as it can. And the rest can be minimal, which won't affect your comfort inside your automobile, right? And the other possibility could be to decouple the parts. So whenever you have more parts attached to each other, you have each part has a different natural frequency, and there's a higher risk of resonance. And the resonance can be really tricky because the excitation of one part can affect another part, and which can in turn result in an amplification of the noise. This is not good. So you can just decouple the parts to eliminate the noise transfer, and so that the natural frequencies are separated and that there is no resonance when they are not connected to each other. Okay, so now coming to the evolution in the field, acoustic testing has evolved significantly in the recent years. And what I'm telling you is, once you are familiar with acoustics, you can see how the microphones, the acoustic microphones for automobile testing looked like before 5 years and how they are today. We have 3D microphones, a lot of microphones which looks like a football, which can capture sound from the area around it. So it's like kind of 3D. It creates a 3D graph of the pressure around it. So it has evolved significantly. This is also because all the OEMs would like to have a quiet vehicle so that they can sell it better, of course. And yeah, as I mentioned, acoustic comfort is one of the key aspects of premium automobile today. So if you buy a car, you expect to sit inside this car and to have a quiet space, even when you are in a traffic, with a high, in an area with a lot of noise, a lot of traffic noise, for example. I remember there was an acoustic scientist. He mentioned that he would like to manufacture a car so that if you are in a traffic, which is very noisy traffic, of course, And you should be able to read a book and have a nice cup of tea, even with a lot of traffic outside. So this is where we are going towards. And then coming to engineers. So for us, the acoustic performance is one of the key challenges. And believe me, there are not many engineers to deal with this challenge. And this is a good thing. Yeah, and today, come to this point, today almost every OEM and supplier has their own in-house acoustic testing facility. This much important it is getting nowadays. And of course, an acoustic test and simulation engineers are in great demand today. And the career path and the job opportunities, acoustics, I think you are convinced that acoustics is a very demanding field, as it is one of the key aspects of the car today, an automobile, and it can be also in an aircraft, of course. The job prospects include acoustic testing engineers and acoustic simulations engineers, as I mentioned before. It's very important and very nice to notice. We have a lot of structural engineers and also with the people with the CFD background. You see them everywhere. So we have enough engineers, but the demand is not that much. So we have more workforce than the demand. But when we come to acoustics, the competition is not at all high. There are very few people who are capable of doing acoustic simulations or testing. But the demand is increasing like anything. And it is increasing really rapidly. So this is really a good career path if you are thinking about moving away from the competition. This is a very good choice. And coming to the main tasks performed by acoustic engineers. As an acoustic test engineer, one performs acoustical measurements of systems, subsystems, and full vehicles, and should also perform on-road tests where you sit inside your automobile and drive on the highway in the night for a few hours and check for the noise coming from the powertrain or wind or road noise, and again the sound transmission loss measurements like an impedance tube or something, for example, and troubleshoot acoustic failures. This is also one of the key aspects, tasks of an acoustic engineer. Even when the automobile is released into the market, customers start to complain about some kind of noise coming from the automobile, and the acoustic engineer should be really agile into jump in and solve this problem. So the troubleshooting is one of the key tasks an acoustic test engineer should perform nowadays. And of course, you should avoid prevent future occurrences of that problem. And coming to the acoustic simulation engineer, should perform acoustical analysis of acoustics analysis, of course, of the system, subsystems, and full vehicle just as a test engineer. And in fact, simulation is not different from testing. Simulation is virtual testing. So, and the additional task of an acoustic simulations engineer is he should assist in concept design. So an acoustic simulation engineer starts much earlier. So even during the concept phase, we need to have a concept. We have a CAD model, CAD model, and we need to optimize it right away. And we have to even perform the failure analysis right away virtually on a simulation model. And then once you have a prototype, then the acoustic test engineer can start working on it. This is a next step. So the simulation engineer starts much earlier, okay? And then the last point, he should, of course, collaborate with both development and testing departments. In case of acoustic test engineer, the collaboration is not, it's important, but not that essential. But in case of acoustic simulation engineer, as he starts much earlier with the design process, he has to collaborate with the development, and he has to follow up about the tests of the prototype, because an acoustic simulation engineer is just not doesn't work on the concept model or the prototype model. Even once you have your parts produced, you have to simulate the parts to check if your simulation matches the test results. Okay, and coming to the acoustic analysis softwares, we have basically, we have a lot of codes, but the basically most used commercial codes are Actran by MSC Software. They're quite advanced. They are located in Belgium, and it belongs to MSC Software. It's a headquarters in USA. But these people working at Actran, it's not a big team, but they have very capable people. They have even, I think, almost 3 professors who have really spent their whole life understanding acoustic. So they are really capable people. That's why you see a lot of new features with every release in Actran. And then we got AVL Excite, a very big company. So they are also investing a lot of money and time in between and acoustic simulations. So yeah, it's just they have also a lot of features, but it's not that much supported as in Actran because they have a very big product portfolio, AVL. So this is only a part of their portfolio. So they are not investing a lot of money into AVL Excite as an Actran. And finally, we have ANSYS. With a good thing with ANSYS has a lot of modules. Like we have a mechanical module, we have a CFD module, which is called Fluent. So in this case, we have a very good collaboration between the mechanical, the structural part, and the CFD part, that's Fluent. So the core simulation, which I just mentioned before, the vibro aeroacoustic analysis is much easier in ANSYS than the other 2 cores. Why? Because they have both cores included within their portfolio, like both structural and CFD cores. With Actran, you can also do a core simulation, but it could be a bit tricky because the structural cores, the structural softwares, which MSC has, they don't have a good compatibility. So every time you have to change something with hand, or it's a lot of work, even then it's not optimal to perform a core simulation. But with ANSYS, you don't have this problem. Of course, it's not the features are not much as Actran, but they are quite capable, especially for vibro aeroacoustic analysis. Okay, and with that, I would like to finish my webinar today. Thank you very much for your attention.